All right, we are about to dive into one of the most incredible scientific stories of our time. It's the quest to see something that, by its very definition, is impossible to see. We're talking about the first ever image of a black hole.
So, right away, you run into this huge, seemingly impossible problem. A black hole's gravity is just so powerful that once you get too close, nothing gets out. I mean, nothing. Not matter, not energy, and yep, not even light. So, if no light can escape it, how in the world could you ever take a picture of one?
You know, that point of no return, it has a name, the event horizon. It's not some solid surface you can touch, but it's an absolute boundary in spacetime. If you cross it, you're not coming back. And that's exactly what makes a black hole black. And it's why this whole idea of photographing one felt like pure science fiction for so long.
Okay, so get this. Albert Einstein predicted black holes were real with his theory of general relativity way back in 1915. For more than 100 years, they were just this wild idea on paper. We had clues they were out there, sure, but actually seeing one, that was the holy grail. The quest was on.
So here's the brilliant trick, the key to the whole thing. You're right, you can't see the black hole itself, it's invisible. But what you can see is its shadow. See, as all this gas and dust gets sucked towards the event horizon, it gets superheated and glows incredibly brightly. The black hole warps the light from that glowing gas behind it, creating this perfect dark circle, a silhouette, right in the middle of all that light. That became the real target.
Now, if you want to see something that's billions of miles away and looks impossibly small from here, you need a telescope with some serious power. The kind of power that would require a lens, well, basically the size of planet Earth. So, how do you even begin to build something like that?
Well, the solution is it's as clever as it is ambitious. It's called the Event Horizon Telescope, or the EHT. And it's not one giant telescope. It's a massive team-up, a worldwide network of radio observatories all working together, perfectly synchronized as one single instrument.
The technique they use is called very long baseline interferometry. It sounds complicated, but the idea is amazing. By linking up radio dishes from everywhere, we're talking Spain, Hawaii, the Chilean desert, even all the way down to the South Pole, they created a virtual telescope. The huge distances between all these separate dishes act as the diameter of this new planet-sized lens, giving it the incredible resolution needed to see the unseeable.
And the logistics are just mind-boggling. First, every single telescope, timed perfectly with atomic clocks, steers at the exact same point in the sky at the exact same moment. Then, and this is wild, they collect so much data, we're talking petabytes, that you can't even send it over the internet. They had to physically fly stacks of hard drives to central hubs. Finally, supercomputers get to work, taking all those separate signals and weaving them together piece by piece to build a single picture. Okay, so they built the telescope. Now they needed to know where to point it. They aimed this Earth-sized camera at the heart of a galaxy called Messier 87, which is home to an absolute monster, a supermassive black hole known as M87 star.
Let's just try to wrap our heads around that distance for a second. 55 million light-years. The light we captured to make this image started its journey to us when giant prehistoric mammals roamed the Earth. It's just an almost unimaginable distance. And the thing itself, it's even more staggering. M87 star has the mass of 6.5 billion of our suns. All of that matter, all of that gravity, squeezed into a space smaller than our solar system. It's one of the biggest black holes we've ever found.
But even though it's so massive, because it's so far away, it looks ridiculously tiny to us. We're talking 42 microarcseconds. To give you some perspective, that is the same as you or I trying to spot a single orange sitting on the surface of the moon. And that is why you needed a telescope the size of a planet. There was just no other way.
So the target was chosen, the instrument was ready, and a global team of hundreds of brilliant scientists was in place. It was finally time to open the shutter, collect the data, and start the long, painstaking journey of turning radio waves into an actual picture.
You know, the actual observation only took a few days back in April 2017. But that was just the start. It took months just to fly all those hard drives to the processing centers. And then it took nearly 2 full years for the science teams to sift through that mountain of data and carefully reconstruct an image.
Now this is my favorite part of the story. To make sure they got it right and to avoid any kind of bias, they did something truly genius. They split into 4 separate teams, and each team had to build the image from the raw data on their own, using different methods. They weren't allowed to talk to each other. The thinking was, if all 4 groups came up with basically the same picture, then they could be sure it was real.
After all that work, after a century of theories and dreams, the moment was finally here. Humanity was about to lay its eyes on the unseeable.
And there it is, this glowing, fiery donut of light. This is it, the first direct photograph ever taken of a black hole's shadow. It's like looking at a ghost of light, all of it bent by gravity, framing the edge of reality itself. 100 years after Einstein dreamed it up, we were finally looking at one.
So what are we actually looking at? That bright ring is superhot gas, plasma, whipping around the black hole at nearly the speed of light. And see how the bottom part is way brighter? That's because that part of the disk is spinning towards us, and its light gets amplified, kind of like the beam of a lighthouse sweeping past. And right in the middle of that ring, that dark patch, that's the shadow. That's the event horizon.
But this was never just about getting a cool picture. This single image unlocked a brand new way to test the laws of physics in the most extreme place in the entire universe.
And this is where it all gets completely mind-blowing. On the left, you've got the real image that the telescope saw. On the right, that's what supercomputers predicted we'd see based only on Einstein's equations from a century ago. Just look at them. They're practically identical. The theory and the observation, they matched perfectly.
From that one image, scientists could pull out some amazing, concrete numbers. They measured the ring's size, confirmed that it was almost a perfect circle, and saw just how dark the shadow in the middle was. And maybe most important of all, they calculated the black hole's mass at 6.5 billion times our sun, which lined up perfectly with what other, less direct methods had suggested.
So why does all of this matter so much? Well, for one, it's the ultimate proof that these supermassive black holes are actually real. It's no longer just the theory. It's also one of the toughest tests Einstein's ideas have ever faced, and they passed with flying colors. And maybe just as important, it's an incredible symbol of what we can do when scientists from all over the world work together.
As the scientists themselves put it, this image turns the event horizon from just an idea in an equation into a real thing. A physical place that we can actually point a telescope at and study. We can now see the edge of forever.
This image really kicks off a whole new age of astronomy. It proves that with enough creativity, enough teamwork, even the things we think are impossible can be achieved. And it just leaves you with this incredible, thrilling question. Now that we've finally seen the unseeable, what are we going to find next?